Professor Travali. So in the previous class, I discussed about field level voltage converter with parallel connection or parallel legs. The next PWM converter, pulse width modulation converter operation. And now in this class, I'm going to discuss generalized technique of harmonic elimination and control voltage control, and also the last concept of first half of the second chapter is converter rating. Okay, these two topics I'm going to cover in this class. Okay, let us get into the topic. So first one is generalized technique of harmonic elimination and voltage control. So actually this is the one effective way to have the freedom of controlling the voltage and also eliminating lower order harmonics. Okay, one effective way to have the freedom of controlling the voltage and also eliminating lower order harmonics is a method pioneered by Patel and Pope in the early 1970s. So these two people introduces this method, effective way to have the freedom of controlling the voltage and also eliminating the lower harmonics in the early 1970s. So it involves varying specific notches. So these are also referred to as chops in the square wave, such that specific harmonics are eliminated from the waveform. Okay, so next, this explained below, like we have so many points to discuss or to explain this one generalized technique. Okay, basically, a square wave can be chopped a number of times in a relationship that eliminates a number of harmonics as well as giving flexibility to vary the fundamental voltage. Okay, so that means in this case I am taking only square wave, that too chopped square wave. Okay, next, so with m number of chops there are m degrees of freedom. So here I am taking m number of chops, that means there are m degrees of freedom. So one of these degrees of freedom can be used to control the fundamental, leaving the other m minus 1 degrees of freedom used to eliminate m minus 1 selected harmonics. So here I am taking m minus 1 degrees of freedom. This is used to eliminate the m minus 1 selected harmonics. So here I am not taking any numerical number. So here I am taking m minus 1 because here m is a number of chops. Okay. Next, so this is the waveform for a PWM converter. So I already discussed this waveform in the previous class in the under the topic of pulse width modulation converter. So the first waveform consists of two types of waveforms. One is sine wave and another one is sawtooth wave. And next, secondly, we have square wave with chopped areas. Okay, with chopped areas. Okay, these two. So it is seen from the previous diagram that a sawtooth wave with 9 times fundamental frequency has 4 notches, each in the positive and negative half cycle waveform. Okay, so if you observe the diagram, you will understand. So from the diagram, here I am taking sawtooth wave. Okay, sawtooth wave with 9 times fundamental frequency has 4 notches each in the positive and negative half cycle waveform. So if you see the diagram, you will understand. So here I am taking a sawtooth wave. So here I am taking 4 notches on the positive side and 4 notches on the negative side. Okay. Next, so they also have half wave and quarter wave symmetry. So they also have half wave and quarter wave symmetry. So it follows that with proper firing angles as well as half wave or quarter wave symmetry, okay, not only the fundamental frequency component can be controlled, okay, but the 3 other selected harmonics can be eliminated. That is 5th, 7th, 11th, and so on. The two from the output AC voltage of a 3-phase full wave bridge. Okay, it is from AC voltage of DC output AC voltage of a 3-phase full wave bridge. Okay, next, so if there were two 3-phase bridges, So assume if there were two three-phase bridges phase shifted as previously discussed in this chapter, that is forming a 12 pulse voltage source converter, then the harmonics that would need eliminating would be the three lowest, that is 11th, 13th and 23rd. Okay, that means 12 and plus or minus 1 harmonic order for a 12 pulse converter. So I already discussed this one in the transformer connections. Okay, transformer connections also I discussed, and the 3-level converter also I discussed this one. So the 12 pulse converter, the 12 pulse voltage source converter consists of 12 and plus or minus order of harmonics. So here these have to eliminate. That means 11th, 13th and 23rd. And with a limited number of notches, it is possible to almost achieve the equivalent of 24 pulse operation with two three-phase 6 pulse converters. Okay, with a limited number of notches, it is possible to almost achieve the equivalent of 24 pulse operation with two three-phase 6 pulse converters. Means that is nothing but 12 pulse. 12 pulse converter. So by using the three-phase 6 pulse, two three-phase 6 pulse converters, that operation is equivalent to the 24 pulse operation with limited number of notches. With limited number of notches. With limited number of notches. And next, on the other hand, it must be mentioned that with PWM operation. So previously I discussed about 3-level converter and transformer connections for 12 pulse and 24 pulse and 48 pulse also. Here on the other hand, it must be mentioned that with PWM operation, nothing but pulse width modulation operation, the higher harmonics will have relatively higher magnitudes than with the single pulse operation. Okay, that means the higher harmonics will have relatively higher magnitudes than with the single pulse operation. Although higher harmonics are easier to filter out. That's why if the higher harmonics are occurred means these higher harmonics are easier to filter out. If the lower order harmonics are eliminated, then with a high pass filter for higher harmonics, a near sinusoidal current flow can be obtained. So here we are using a high pass filter for higher harmonics. That means whenever the lower order harmonics are eliminated, next we are coming to the higher order harmonics. So if you want to eliminate or reduce the higher order harmonics, we have to use the high pass filter. So here a near sinusoidal current flow can be obtained. So with 3 notches per half cycle, one can eliminate the 5th and 7th harmonics from a 6 pulse converter, or eliminate the 11th and 13th from a 12 pulse converter. 12 pulse 6 pulse converter, sorry, 12 pulse converter. Okay, so you know already the order of the harmonic for a 6 pulse converter is 6 7. And next we have 12 pulse harmonics, 12 pulse converter means we have 4 and plus or minus 1 order. Okay, and next, so I already said that figure 3.11 means previously I shown the PWM converter waveforms. By using this, the diagram conveys a generalized half-wave output waveform with m notches defined by angles alpha naught, alpha 1, alpha 2 and so on, alpha 2m plus 1. Okay, these are the angles we are used for the waveforms alpha naught, alpha 1, alpha 2 and so on, alpha 2m plus 1 with angles alpha 1 and alpha 2 defining the first notch, alpha 1 and alpha 2 defining the first notch. So with 2m is equal to 9, with 2m is equal to 9 in the example of figure in the 3-level converter operation. So in that one, m is equal to 4 representing 4 notches per half cycle. Okay, understand? M means notches. Okay, so here I am taking 2m. So that is 2m is equal to 9. So if we take m is equal to 4, that means 2 into 4, that is equal to 8. Okay, so that representing 4 notches per half cycle. M is equal to 4 means that representing 4 notches per half cycle. If we take 5 notches per half cycle, and 6, it representing 6 notches per half cycle. Like that we will have. Okay, next, So the generalized waveform of AC voltage for a phase leg has a voltage amplitude of plus Vd by 2 and minus Vd by 2 with respect to the DC midpoint. That's why I am taking the voltage with respect to the DC midpoint is VAN, VA capital N, not small n. If you take small n, it is coming under the transformer neutral connection. But here I am taking capital N means it is the neutral DC midpoint. Okay. Next, assuming Vd by T is equal to 1 per unit for generalization and half wave or quarter wave symmetry as in the AC voltage waveform of figure 3.11, that is nothing but PWM converter operation. Okay, so the waveform can be represented by a Fourier series as, so I already discussed this one. By using Fourier series we will discuss the functionality of any harmonic order, that is f of omega t, that is equal to sigma n is equal to 1 to alpha an sin of n omega t plus bn cos of n omega t. This is the equation representing the waveform of pulse width modulation. Okay, next, so where with half wave and quarter wave symmetry we will take bn is equal to 0. Okay, and m minus 1 equations can be assigned for the specific targeted harmonics. That means to be eliminated as an is equal to 0 for these harmonics. That's why we will put both are zeros. An is 0 and bn is 0. That's why here I am taking an is equal to 4 by n pi into 1 plus 2 sigma k is equal to 1 to m minus 1 whole power k cos n alpha k. This is the equation I am taking. So here the first equation is f of omega t is equal to sigma n is equal to 1 to alpha a n sin n omega t plus bn cos n omega t. So but this one bn is equal to 0 I am taking, so we will have only an value. So we will expand this an value by using sigma n is equal to 1 to alpha. In between n is equal to 1 to alpha I will extend, so that the equation will become, this is n is equal to 4 by n pi into 1 plus 2 sigma k is equal to 1 to m minus 1 whole power k cos n alpha k. Okay, so here m minus 1 equations can be assigned for the specific targeted harmonics to be eliminated as an is equal to 0 for these harmonics. So the remaining one equation is used for a specific required value of the fundamental voltage with a1 is equal to a finite per unit value, a finite per unit value. Okay, next, so by solving these equations, that is f of omega t and an values, one can obtain specific values of angles alpha for a specific value of the fundamental voltage. Okay, next, thus for 4 notches per half cycle. So if you consider 4 notches per half cycle as from the figure 3.11, there will be 4 equations to be solved to calculate all values of a for turn on and turn off pulses corresponding to each discrete value of fundamental voltage. So we need 4 equations to solve the 4 notches. Why? Because to calculate the all values for a turn on and turn off pulses corresponding to each discrete value of the fundamental voltage, and these are non-linear equations and would require large amounts of real-time iterative computation, and there may be more than one solution for some values. More than one solution, that means one or more. Okay, or given to some values. Okay, next, thus it is preferred to use lookup tables for say each 0.5% change in the magnitude of the required AC voltage. Okay, thus it is preferred to use lookup tables for say each 0.5% change in the magnitude of the required AC voltage. So the required shift in angles for the required AC voltage variations per step is quite small, and the number of steps can be reduced and the change from step to step is linearized. Okay, here I am taking required shift in angles for the required AC voltage variations per step is quite small. So here the number of steps can be reduced and the change from step to step is linearized. Okay, so these are the generalized technique of harmonic elimination and voltage control, and we have some few more points to discuss. So clearly with the digital controls, this method is superior to the sawtooth sine wave control or any other wave comparison method. Okay, that too with digital controls only, not manual controls, not analog controls. So clearly with the digital controls, this method is superior to the sawtooth sine wave control or any other wave comparison method. And the AC fundamental output voltage can be controlled over a wide range down to perhaps about 10% without excessive distortion of the current flow or need for a large harmonic filter. Okay, so here I am taking AC fundamental output voltage. So these can be controlled over a wide range, that to 10%, without excessive distortion of the current flow or need for a large harmonic filter. Okay, next, coming to the last topic in the first half of second chapter, that is voltage source converter and current source converter. So here, converter rating. So here we are using general comments to this topic. So here, before going to the converter rating general comments, we will have some points, that is assuming that the required converter rating is rather low. So just for assumption, the required converter rating is rather low. The least cost and simplest controllable three-phase converter would seem to be a six-valve converter with one turn of device or diode per valve. So, okay, here the six-valve converter with one turn of device or diode per valve is used to control the simplest controllable method, okay, for three-phase converter, and it that also least cost. Okay, so in fact applications there will usually be a need for a transformer between the converter valves and the AC system. So you already seen these things in many diagrams in these voltage source converter topics. So on the DC side we don't use any devices, only DC capacitor we will use, and on the AC side, that means on the right side of the diagrams, we will use converters, and these converters are connected to the transformer, that in the AC side. Okay, there is therefore a certain flexibility provided by the transformer turns ratio. Why? Because to match the available device current and voltage ratings. That's why we are using the transformer ratio, turns ratio. Okay, it will give a flexibility. Okay, next, a 6-pulse converter based on one device per valve could yield a maximum rating of say 5 MVA. Okay, here I am taking 6-pulse converter based on one device per valve. Okay, could yield a maximum rating of say 5 MVA. So however, even at this low rating, a simple 6-pulse converter is unlikely to be the best choice for connection to the AC system on account of harmonic distortion requirements. Okay, and next, complex decisions have to be made on the use of large filters versus higher pulse order and PWM or quasi PWM converter topologies, etc. Okay, etc. Apart from the flexibility required for the control. Okay, here we are taking complex decisions. Why? Because if you use the large filters uh, in higher pulse order and pulse width modulation or passive pulse width modulation topologies, these are apart from the flexibility required for the control. Okay, next, so one area of needed attention for single device per valve converters is the consequence of failure of a device. So previously I said that we use single device per valve, but if you use single device per valve converters is the consequence of failure of a device. So that's why we use of fuses would not be desirable. So at the time if you use the fuses, this also not desirable. However, given the advances in sensing and digital production technology, it is not unreasonable to sense a fault event, including a shoot through in a few microseconds and turn off other associated converter valves for an effective safe production strategy. Okay, here we are using fuses, so these fuses would not be desirable. Why? Because given the advances in sensing and digital production technology, it is not unreasonable to sense a fault event. That means it includes shoot through in a few microseconds and turn off other associated converter valves for an effective safe protection strategy. So most tax applications will involve converters with a rating much higher than 5 MVA. Okay. Next, the designer now has many options to meet the needs of the higher rating. Okay, the designer now has many options to meet the needs of the higher rating. So these options, so up to now we discussed about lower rating, and now the designer looking onto the higher rating. So here a few points is there, few options. Okay, in those things, first one is increase pulse order to 12, 24 or 48. Why? Because in order to reduce the harmonics to an acceptable level with 2, 4 or 8 6 pulse converters. Here 2 6 pulse converters means this is nothing but 12 pulse converter, and 4 6 pulse converters means it is nothing but 24 pulse converter, and 8 6 pulse converters means it is nothing but 48 pulse converters, and duly phase shifted. Okay, one can concurrently increase the total converter rating to a maximum of 10, 20 or 40 MVA. So previously we discussed about 5 MVA, up to 5 MVA. So now we are discussing about maximum of 10, 20 or 40 MVA because of increasing the pulse order. Okay, and we are also taking the converter rating in a high manner. Okay, still with one turn of device per valve. Here also we are using one device per valve, that is turn off device. Okay, next, so here one is faced with the choice of series or parallel connection on the DC side. Okay, types of transformer arrangements and phase shift among converters, and series or parallel connection on the AC side. So it is on only one side. Okay, and next these approaches have to be balanced with the other means of reducing harmonics and acquiring flexibility of dynamic and steady state controls, including 3-level and PWM and special notches and combination of the above. Okay, 3-level PWM and specific notches and combination of the above. And next, second point is, that means second option is adopting a 3-level converter topology. So here I am adapting 3-level converter topology. It doubles the converter voltage and hence the potential maximum single device per valve. Per valve converter capacity to say 10 MVA per 6 pulse, 20 MVA per 12 pulse and so on. 10 MVA per 6 pulse, 20 MVA per 12 pulse and so on. Like this, the capacity of the converter, so capacity of the single device is increasing. Okay. Next, so the 3-level topology provides the flexibility of a limited range of independent AC voltage control. Okay, but again, this has to be balanced against the low frequency PWM or notch based topologies to achieve independent AC voltage control. So thus it is seen that a modest size FACS converter rating can be achieved without having devices in series. And coming to the third option, so connecting devices in series is the most frequently used option for high power converters. You already know this point. So here the issue is that of ensuring equal voltage distribution among the devices. This is the main issue. Okay. Next, while the series connection technique is well known, voltage dividers or snubbers have to be provided, and some allowances has to be made in the device voltage rating. That means it is also a practice to include one extra device or diode in series in each valve to ensure continuation of operation in the event of failure of a device. If we take the series connection, okay, there is a chance of failure of device, so that's why we are taking extra device into the system. So note that when a power semiconductor device fails, okay, it must fail into a short circuit and continue to carry current indefinitely without adverse consequences, other than the fact that failure of a second device or diode in the same valve could lead to a catastrophe. Okay, and next, double the number of phase legs and connect them in the parallel. This is shown in figure in this one. So actually this diagram is used in the 3-level converter operation in parallel connection with parallel legs. Okay, in the topic I used this diagram. Okay, so here I am telling that double the number of phase legs. So actually we are using one phase leg, but if you want to connect parallel 3-level converter, so we use this diagram. Okay, and connect them into parallel. Okay, in which the two phase legs are connected in parallel via a center tapped inductor. So in between the phase legs we used one center tapped inductor. Okay, these phase legs may be of the 2-level or 3-level variety. Okay, next, fifth one is connect converter groups in parallel. Connect converter groups in parallel. So why? Because in fact a large number of groups can be connected in parallel beyond what may be needed for increasing the pulse number. So if you connect the large number of groups in parallel, so this needed for increasing the pulse number. So if we increase the pulse number means we have to increase the converter rating for the given device. Okay, with parallel connection of converters, it is necessary to have a protection strategy. Why? Because it oscillates a faulty converter with minimal impact on the operation of the other converters. Okay, and a 48 pulse converter with all 6 pulse converters, that means 8 6 pulse converters connected on the same DC bus involves 24 phase legs in parallel. 24 phase legs in parallel. Okay, next, so with high speed sensing and fast turn off capability of devices, parallel connection of large number of phase legs is quite feasible. So if you use high speed sensing and fast turn off capability of devices, parallel connection of large number of phase legs is quite feasible. However, considerations of fault currents, high current bus work would often lead to a combination of series and parallel connections. So actually we taken that series connection as a separate and parallel connection as a separate, but if we take in the considerations of fault currents, high current bus work would often lead to a combination of both series and parallel. Okay, and coming to the last point, use a combination of 2 or more of the options. So actually I discussed 5 options. So by using among the 5 options, we use the combination of 2 or more of the options mentioned above or any other option not mentioned above. So if you have any idea other than these 5 options, use that one also in order to arrive at a converter of required rating and performance. Okay, next, so also given the high relative cost of high voltage isolation with the transformers, there is a strong incentive to somehow come up with a platform based design and even transformer less design, particularly when a small converter is needed in a high power transmission. So we use high relative cost of high voltage isolation with transformers. Why? Because we need strong incentive. Why? Because to come up with a platform based design and even transformer less design also, that too when a small converter is needed in a high power transmission. That means it is obvious that a designer, that means supplier, has a large number of options to sort out. If two design teams worked separately, the odds are very much in favor of them arriving at different solutions. Okay, and next, it is therefore important that the purchaser of fax technology pay more attention to the performance specifications rather than to details. Okay, rather than to details of the technical design. Okay, so thank you. So this is the first half of the second chapter, that is voltage converters. In the next class I'm going to discuss second half of the second chapter, that is current sourced converters concepts. Okay, thank you.